I will pause. I don't plan on going past 7:30, so hopefully that works out good. I can cut it shorter too. I am a meteorologist at the National Weather Service. We are part of NOAA, National Oceanic Atmospheric Administration. And it's always fun doing these presentations because it seems like whenever I do a presentation on climate, we have weather. In other words, we have rain, we have hot weather, we have windy conditions, we have snow in the mountains. It seems like those things always happen when I talk about climate. But it's important with climate talks not to relate it to the current weather. And you might be wondering why. And don't worry, my mom does it too. And I've pretty much given up on trying to tell her otherwise. But when we talk about climate, we're talking about long-term kind of accumulations of weather. And we're talking about 10 years of data or 20 years of data, in some cases, hundreds of years of data. And all these weather events that we have, whether they're big, small, they add up to what we call climate. In this particular talk, we'll talk about some extreme events, and that could be hot or cold, that could be dry or wet. We'll talk about some seasonal events like summertime, a year of weather, 5 years of weather, that type of thing. We'll talk about anomalies and records as they relate to weather, and also talk about climate and climate trends. Because ultimately, what we're all really asking is the climate changing? I know we talk a lot about weather events. Oh, wow, that hurricane was massive. Or we had a drought last year and it never rained. Or it was so hot in August, that our air conditioner bill was $1,000 type of thing. But what we're really all asking and wondering about and really trying to project are things changing. Long-term trends. My kid, I have 2 teenage kids, and I can joke with them about weather and about climate and stuff sometimes. And I tell them, boy, when I was little, the snow was really deep. By the way, I didn't grow up in Southern California. I grew up in New England, Vermont, of all places. So I have lived and worked in several different locations, including New York, Virginia, Texas, Utah, and of course, California as well, where we're stationed here in Rancho Bernardo in Southern California. So I could joke with my kids and, tell them, even though I'm 100% joking and not being scientific at all, but it did seem like the snow was deeper when I was little. Maybe it was because I was little, maybe not. But when we talk about climate, we try to put it in an objective kind of scientific context, and we need to be careful that we're not just talking about it, that we're actually looking at the data, looking at the numbers, and referencing those. And if it really was deeper snow when I was a kid, then that might be a trend, and that might be really what we're getting at in a situation. So we're not going to talk about Vermont and trends. We're going to talk about California and trends in general. But it's important to look at different type of weather events that occur that make up our climate. Believe it or not, some of those weather events that are most significant, most deadly, that make up our climate here in the United States or here in California, heat is the number one. So why is that important, that heat's the number one weather-related disaster, weather-related killer? Because temperature and temperature trends are ultimately one thing we're talking about often when it comes to climate change, global warming. Now, the other events are important too: flooding, lightning, wind, cold weather, all different types. But it is interesting to me and often to others that when you look at a 10-year average, a 30-year average of different weather, probably the most boring weather event that you can have might be heat. But unfortunately, heat is important because it is fatal. And it is one of those kind of, you might call it a silent killer type of event. And it exceeds our classic events like tornadoes, flooding, hurricanes, those type of things. The ones that everyone talks about and sees on the news, heat is actually the #1 killer on average. Now, when you look at disasters all around the board in terms of the dollar bill, how much do they cost us, taxpayers? How much do they cost the government? How much do they cost the private sector? You can kind of pile those all up and see that in the past decade or so, the combination of boring heat and drought, the combination of exciting and scary tropical weather like hurricanes, the combination of what seems to only occur in California, right? Wildfires. When you add up all the different weather events, you can start to see a trend. Of course, you adjust it to inflation. Yes. When you look back the past decade or so, you can actually see a trend where billion-dollar disasters are increasing. They might be the hurricane, they might be the flooding, they might be the drought like we suffer in California, or they might just be severe storms like hail, wind, lightning, those type of things. No matter what it is, when you add them all up and look at the cost or the amount of money that has, been spent to recover or to deal with these disasters, the trend is definitely going up. And when we talk about climate and climate extremes, that's important. It's not fair to talk about one event. It's not fair to talk about one type of event, but you have to talk about all those events, all the different events, if you really want to start saying that there's a trend or there's a change. You can look at it this way as well. This is just maybe a prettier type of graph with more vivid colors, but it is important to look at, beyond just classic weather like hurricanes and flooding, hurricanes and wind. Wildfires are increasingly important and adding to those billion-dollar disasters, but so is drought. Drought's also adding or contributing to these type of disasters. Now, when you look at the past recent years and you kind of categorize it, what year is the worst? What year have we spent? When we turn on the news, it says this year's the worst. When we turn on the news next year, it says this year's the worst. But what years really have been the worst in terms of billion-dollar disasters? You can see 2017 stands out. $340 billion of combined disasters related to drought, wildfire, heat, hurricanes, tornadoes, thunderstorms, you name it. All the different weather types. The weather that we don't think of as weather, which is drought and heat, or the weather that we think of as weather like hurricanes and tornadoes. 2005 made the top, 2012, and then you can see 2021 is not far away. There is considerable separation, though, compared to what happened in 2017. Just an awful year when it came to billion-dollar disasters, 2017. When you look at 2021, because it's always about what have you done for me lately, right? Our memories are relatively short, and that's why you can't trust my memory, right? Of when I was a kid and the snow seemed deeper. That's a long time ago. But in 2021, you can look at billion-dollar disasters and see there's plenty of them. Why 2021 has made it so high up on the list. In California, it was flooding back in late January. That was a big atmospheric river. Mostly missed us in Southern California. And then you cannot forget, of course, we just came from it, the worst wildfire season in terms of acreage burned in California history. And that was just this past summer, 2021. We also have ongoing drought making 2021 significant. How much drought? Well, Lake Mead reached an all-time low on its reservoir in 2021. So did Lake Oroville, which is Northern California. I won't bore you with the rest of the United States, but you can kind of see the symbols on there, and that's your classic weather that was extremely significant in 2021. Hurricanes, thunderstorms, and that type of classic weather. But out west here, back-to-back years of extreme wildfire activity. 2021 trumped 2020. Back-to-back years of drought. Well, when you add up drought, you don't ever really get anything better. So adding up 2 years of drought makes it worse than the prior year. And believe it or not, mixed in all that, a major flooding event in late January in South Central California. That was the one that closed Highway 1, basically washed it off the side of the hill. If you're having trouble remembering that event last year for rain. All right, how about some weather events in recent years that are a little more local in Southern California? So 2021 in the books is the hottest summer, and we're not quite done yet, the hottest year on record for many places in Southern California. Those would include Palm Springs, those would include Idlewild, Big Bear, and also Anza Borrego area in San Diego County. I picked those points just as reference. Obviously, we don't just look at 1 or 2 points and say it's the hottest year on record in the deserts, but those are 2 points that have a lot of climate data, a lot of history. Recently, just a year ago, we said the same thing in 2020, but it also was the hottest on record for the whole entire state of California between the month of June and October, which is basically summer for us, all intents and purposes. You could look at other temperature statistics. Just a few years ago, the last drought we had was the warmest and driest on record. The 2017, remember I mentioned 2017 to 2017-18, that winter was the second driest on record for our region in Southern California. So it kind of goes on and on and on. You can see different statistics on there. What about for rain or lack of rain? 2019, we saw the wettest one-day rainfall in places like, someone mentioned Palomar earlier, places like Palomar Mountain and Idlewild. In February 2019, they had their wettest on record one-day rainfall. But just a couple years, prior to that, we were dealing with severe drought in that 2017-18 year. In 2017, we also saw some historical rain. We saw the San Diego River reach its third highest water level, which was about 14 feet. And we also saw some record rainfall in early December 2018. Now, just recently, or a year ago, in April of all months, April doesn't usually rain a lot in April, April 2020, northern San Diego County, which I know most of you are just north of that, but northern San Diego County had its most rainfall in a 24-hour period as well. Not just Palomar Mountain like I showed in 2019, but in 2020, April, 3 to 5 inches of rain, the most rain ever recorded in Encinitas and Oceanside, occurred on April 10th. It set an all-time record for the amount of rain that they've received in a 24-hour period. So the bottom line with all this is all these different extremes, they are certainly impressive. The one thing we have to look at closely is, are they a trend? Are we seeing trends of more of these? And are these trends changing our climate in terms of long-term averages? And that's really ultimately the big question. Can we blame it on El Nino or not? Well, some of these recent years of El Nino have been dry, some have been wet. Some of these recent years of La Nina, which is the opposite, have been dry, have been wet. So we can't easily attribute it and, so to speak, blame it on El Nino or blame it on the opposite, which is La Nina, because we're seeing different results. We're seeing different outcomes. We're seeing dry years. For example, remember I mentioned 2017, 2018? Well, that was a pretty wild year. But San Diego received 3 inches of rain, which was almost the driest ever year on record, and that was a La Nina. But the year before that, we had a La Nina, and San Diego had 13 inches of rain. So we cannot blame it on El Nino. We cannot blame it on La Nina. Something else has been going on or is going on that is resulting in these extreme individual years, whether it be dry or whether it be wet. A lot of times I get questions, did you look far enough back? How far back do you look when you talk about climate and climate trends? Did you look 10 years? Did you look 30 years? Did you look 100 years? Well, you're not looking further enough back. However, the state of California has invested a lot of money through the Department of Water Resources, and they are looking back. They are looking back 100 years, 1,000 years, 3,000 years. They're looking back as far as they possibly can with where there's reasonable data to better understand, are there trends? Are we seeing trends with temperature? Are we seeing trends with drought? This example up here shows the Sacramento River and the Colorado River Basin, where we get almost all of our water from, the two. And it's a bunch of noise, but it's usable data where we can actually look back and see if there are trends. So the short answer is yes. And yes and no. No, we're not just looking at the past year and saying, well, we're seeing warming, we're seeing drying, we're seeing more extreme weather. We're looking back as far as we possibly can. So that brings up the point of normals. So believe it or not, every 10 years, just like the census, NOAA, National Weather Service, develops new normals. We just did it in 2021. We just released brand new normals. Now, what is a normal? A normal is a 30-year average of weather. And some of that weather might be extreme. Some of it may be very benign and boring. But it's a 30-year average of weather. So every 10 years, just like the census, I'm sure you fill out the census, right? You probably don't get anything in the mail asking you about weather, but every 10 years it's updated. And what we saw with the most recent update is there are changes. And so that is ultimately, that's really what you're asking when you talk about climate. That's really what scientists are asking. That's really what everyone is asking. They may not realize they're asking that, but what they're asking are there changes. They may be joking and saying, well, it's the new normal. Oh, well, it was raining yesterday. It'll be sunny tomorrow. But deep down inside, what they're asking, are there changes with our normals? So you can see on the left-hand side, the brown is showing where our normals have significantly become drier. The dark green are where our normals have significantly become wetter. So you can look in northern Vermont, for example, where I grew up, pretty dark green. So it's indicating it's becoming much wetter. You can look where I live now in San Diego, and it's becoming much drier. So what this is showing is when you average the past 30 years, which is what a normal is, how has it changed from 2010 to now 2020, or when these was released in 2021? And you can see much drier. Now on the right-hand side, it should get your attention. So despite where I grew up in Vermont becoming much wetter and where I live now becoming notably drier in the past 10 years, when you compare the changes in the normals, almost everywhere in the United States is warming, and not just warming, but significantly warming. 1 degree of temperature. My daughter is 14 years old, and she's taking a class in high school. I don't think it's an earth science class. I think it's a biology class, and they're learning about climate and climate change. So I get kind of briefed every once in a while, and even recently, where she'll tell me, you know, Dad, 1 degree Fahrenheit of warming over 10 years is significant. And so I basically respond, oh, is it? That's good to know. Is that happening? And she says, yeah, that is happening. We learned that in class. Well, on the right-hand side, not only is Southern California, but it's almost the entire West, and also New England, Florida. And there's one area in the Midwest and Tennessee Valley that looks like they have been spared some of the more severe warming, at least over the past 10 years. And they also been a little bit
Can I ask
wet.
a question? Can I ask a
Yeah,
question?
go ahead.
What is it? What in the legend? It says 91 through 2000 minus 1901 to 2000. So the minus includes the incorporated. So can you explain that?
So the new normals go from 30 years, which is 1991 to 2020. And what it does is it subtracts the century average. So it takes the past 30-year normal and compares it to the longer term century average. Often I get the question, well, why don't you do 100-year normal? Why don't you do 100-year normal? Why do you only do 30 years? If you have 100 years of data, why don't you do a 100-year average versus a 30-year average? And it's a legitimate, good question. But the short answer is, if we were referring or referencing a 100-year normal, we'd be breaking records all the time, every day, because the 100-year normal or 100-year average is much, much cooler. So what you're looking at there is the new normal, the past 30 years, compared to the longer term 100-year average. Does that make sense? Does that
Yeah,
explain your
it
question?
does. It does. Thank you very much.
Okay. And so the century, and that's really what the title says up top, change compared to the century average. The new normals are much warmer across the entire country, and across really all the United States, and our region much drier. If you look at the 30-year average and kind of plot them, so let's pretend it was early 1900. Okay. And you were watching the news and they said, well, the normal high is 61 and today's high was 70, much warmer than average. Okay. So that would be the upper left-hand corner. That would be the early 1900s. And then you go forward and you flash all the way to our most recent normal. You can see that in the early 1900s, compared to the 100-year average, the same question that was just asked, in the early 1900s, we would actually be cooler than the 100-year average, the blue shaded. Right now, on the lower right-hand side, the same map as I showed before, we are much, much warmer than the 100-year, or whatever you want to call it, century average. So you can kind of step through, you can pick your favorite location, probably Southern California. You can step through and see each time those normals were updated compared to the century average. Of course, in 1901, you didn't have the century average. So this is done after the fact, but you do have the 30-year average back then. So you have cooler, cooler, cooler. Then it kind of balances off in the 30s and 50s. And then you get into the 40s and 60s, and it's kind of still neutral. The 50s up to the 70s, and you see a little bit of warming in Southern California. Then the 60s into the 80s, where a lot of us have spent a lot of time probably. You can see there's considerable warming in Southern California compared to the century average. And then you go to the 70s to the 90s, the 30-year average there, you can see quite a bit of warming. And then it's really noticeable, or should be, once you go to our most recent normal, which was 81 to 2010, to what our current normal is, 1991 to 2020. Might take a little bit to digest, but the bottom line is we are seeing those warming trends, those 30-year averages. The definition of normal, I didn't make it up, but the definition of normal is a 30-year average. And I commonly get the question, well, why don't you use 100-year average? Be careful what you wish for. If we used 100-year averages, 150-year averages, we would be astonishingly above normal, much, much warmer. It'd be pretty astonishing to you on a regular basis, not every day, but on a regular basis. So this past summer, we would have been shattering records. We already broke enough records as it was in terms of being the hottest summer on record for some of the mountains and desert areas in Southern California, but it would be even worse. I hope that makes sense. And because we have identified that there are significant trends, the normals are now being looked at every 10 years on a 10-year average. So the idea behind this is the normals are changing every 10 years. When you recalculate, you got a whole new 10 years of data into your system, so it's like you go on vacation and you made a lot of transactions and you go recalculate. Oh, shoot, my savings account is a lot lower. So in this case, every 10 years, we do the normals. But there's been such dramatic changes over the past 10, 20, 30 years that we now have a 10-year normal to help track that better. So we have a 10-year normal to help track that better. And that shows that severe drying and warming over Southern California and the desert Southwest. So what this is showing here is something, rather new. This was a request, on popular demand, if you will. So since we're going through the trouble of recalculating normals every 10 years, why not examine that trend that might have occurred and what a 10-year actual, normal or average might be. So it's just a way to, kind of fine tune what is being identified as a trend, how real it is, where is it most severe, that type of thing. There actually is a area in, if you're thinking of moving, North Dakota, South Dakota, where the past 10 years, there really hasn't been much trend at all. And the 10-year average is pretty much status quo, stable in that area. But other than there, most areas just continue to see that warming. In California, the fall period warming, and again, what are we looking for? Are we pulling straws out of a hat? Are we trying to find one storm that fits our story well? No. Now, when it comes to drought, climate, long-term trends, whether you define it as 1 year or 50 years or 1,000 years, we're looking for those trends. And one of the trends that is coming up is the fall period, what we consider fall, September, October, November period. This map here shows October, which is a critical time in California on any given year. 3,000 years ago, it was critical, and this year it's critical because of our normal dry season. In October, we tend to be just barely coming out of that. So the vegetation is very dry in October. And you can see the warming and the notable warming in the desert south. Longer summers is the bottom line. You can see that in November, it's even more widespread where the warming is occurring. And then when you get into December, it kind of shifts. It stops taking focus on Southern California and a lot of the West and takes over most of the United States, where you're getting warmer winters, at least the start of the winter, as shown in the lower right-hand side. And in California, the bottom line is you're getting longer summers. The summer isn't getting longer. The calendar is the same. But the climate or the weather that makes up that climate is getting longer, and you're having longer fire seasons. We just saw it right now. Not ideal to just look at a recent example, but the month of December had zero precipitation. Month of November had zero precipitation, and it was record warm for much of areas like Big Bear, Idlewild, Palm Springs. Much of our mountains and deserts were record warm. Riverside was top 10. And the last time we saw that was 2017. I mentioned 2017, I think, didn't I? The last time we saw that was 2017, having no rain in November. And we've only seen it about 6 or 7 times in the past 150 years. So pretty significant. But it does match the trend that we're seeing with these drier falls, longer summers, shorter winters. So in essence, a trend is being identified, and it is concerning. Let me show you a couple weather maps here. So a couple years ago, we had a pretty active winter, 2019, 2020, pretty active winter. And we had several storms that moved through Southern California, and they were very wet. I shared one of them, with you. The April 2020, that was record breaking in San Diego, April 2020. record-breaking rainfall in San Diego from that one set of storms. But one thing that happened 2 years ago in that winter was a massive area of warm air up where the airplanes fly, 20, 30,000 feet, not where we live, but up where the airplanes fly. No one's living over the Pacific Ocean, but up in the upper atmosphere, this massive dome of high pressure, or whatever you want to call it, warm air, developed. And it sat over the Pacific for the entire winter. And that was year one of the drought in Northern California. So that was the start of NorCal's drought. But somehow, miraculously, we were on the very edge of that storm track, and we had a pretty wet winter that winter in 2019 and 20. The following year, which would be last year, that same anomaly, and what I mean by anomaly is what we just talked about. It's a departure from long-term averages. And so where all those orange, red shaded areas are is saying that the atmosphere is much warmer than a long-term average. And this is a whole winter average. So this is October all the way through March, all averaged together, divided by the number of days, whatever. And the problem with last year was that same area was there. So the atmosphere never reset. Things didn't start over again like a new season. And not only was it still there, it was broader and it shifted east. And that was year one of our drought in SoCal. We only had 4 storms. They're listed on there. 4 storm cycles. And that was year 2, and what ended up being and making the lowest water levels on Lake Oroville, the lowest water levels on Lake Mead, and so forth. And the 2 back-to-back years of just astonishing fire weather or fire acres burned last year and the year before. So the question is, again, is it a trend? Are we seeing a trend in the weather pattern? Is the weather pattern shifting north? Is the jet stream retreating north? Not just one day, not one storm. Who cares about that? That's weather. That's weather. Weather is an imbalance on our planet. That's all good. That's all good. Weather is cold, warm, dry, wet. That's what makes the jet stream, that black line. That's what makes weather when you have differences. That's all good. But in this case, are we seeing a trend since it lasted the whole entire year before, and it's lasting the whole entire prior year, 2020, 2021? If you look at this most recent year, you can see that on the left-hand side, how dry was it? The dark red areas were driest on record. The brown, orange areas, depending on how it's showing up on your screen, were top 10. So the lowest 10 percentile, much below normal across all of California. And on the right-hand side shows the percent of normal. So compared to normal, you can kind of see, I hope now, how important normal is and how normal is calculated and referenced it. On the right-hand side, you can see the LA basin last year was literally 30% of normal. The Northern California area had a lot of areas that were about 30% of normal. The bottom line was 2021 was very dry, and in some cases record dry across South Central and Northwest California. So I'll pause there before, I don't know if we'll have time much to go into the fire season, but let's open it up and see if there's any questions about the important topics that we talked about: climate normals, climate trends, and just plain what we're observing with the climate over the past years.
Yeah, thanks, Alex. I'll look at the chat here and I can see that I think it was Leslie, let me look here, that asked, yeah, right in the beginning, the prediction is that the Western US will be cooler this season and the East will be warmer. Please shed some light on that. So I don't know if you've heard that or not.
So that's kind of, thanks for the question. And I will go to, are you still seeing my screen? Hopefully.
Yeah.
So it was a little bit choppy on your bandwidth there, but I think the question, I'll repeat it, I'll paraphrase, was that this upcoming winter the prediction is expected to be cooler in the West and warmer in the East.
Yes.
Yeah, that was on the news tonight. Yes. Yeah, that's the map they had. Yeah.
Okay, so this forecast was actually made a couple weeks ago. We use this in a lot of our weather briefings. And so what this is it's a forecast for December through February. Why do they choose December through February? Because that's the core of the winter. That's the astronomical meteorological winter. That's when, you know, when most winter type things happen, like snow and cold, that's when they occur. And the prediction for Southern California is warmer than average and drier than average. We don't care as much about the warmer than average, but it does play an important role in water supply. So we have to care about it more and more because just being a little bit warmer than average can end up meaning a shorter winter, like I showed earlier, a milder winter, and less snow, less manageable snow. So let me give an example, to put it in context. So right now, today, at 7,800 feet in Lake Tahoe, I assume some of you probably really good with geography and probably been to Lake Tahoe area a lot. But at 7,800 feet at Lake Tahoe, there's 9 inches of snow. Probably doesn't sound like much, does it? After this storm cycle moves through, the one coming next week, that 9 inches could very well be 65 inches. So they might get 5 feet of snow or close to it, 4 to 5 feet of snow at that elevation of 7,800 feet. So how do I know that? Well, I get an email every day from Sugar Bowl Ski Resort, and they measure the snow there. And if I don't believe them, then I tell them to take photos. But I usually don't do that. But so this year is starting off incredibly dry in terms of the snowpack because it's been so warm, so mild. This past summer, Boise, Idaho, Salt Lake City, Utah. I picked locations before. Remember, I mentioned Palm Springs had the hottest summer on record this past summer. But Boise, Idaho, and Salt Lake City set the most number of days over 100 degrees this past summer. So it's not just Palm Springs. It's not just Palm Springs. It's not just Lake Tahoe. It's a lot of areas that are setting these records and seeing this trend. But where am I going with that? So one of the things we look at with climate is not just the trend, but we look at the extremes. So if you have one year where it's really wet and then 1 year where it's really dry. What's the average of that? The average of that is, in between, and it's not that bad. But if you continue to have, years that are really wet, really warm, really dry, really cold, that type of thing, your averages start having more meaning to them, because you just have so many extremes in there. So that's the type of thing we look at is, we're getting more extremes. It's more difficult to manage when all the rain comes in 1 month, when all the snow comes in 2 months, when you may not know this, but in late October, Sacramento, California had set a record for the most consecutive days of no rain. So remember, I told you that Northern California has been in 2 years of drought, back to back, 2 years of drought. Sacramento set a record for the most number of days of no rain. Whoop-de-doo, right. The next week when they set that record, they got 5.3 inches of rain. That was October 25th of this year. 5.3 inches of rain in 1 day, 24 hours. Why is that a big deal? That's the most rain they have ever recorded in Sacramento in 1 day. I gave you some examples earlier of Idlewild in Palomar back in 2019, where they set their daily record of about 8-9 inches of rain. And then I gave you an example of northern San Diego County, where they, in April 2020, where they had the most rainfall, 5.5 inches in Encinitas in 1 day. So when those are just weather events. Those aren't climate, but those are just weather events. Those are extreme weather events. And when those type of events happen, we deal with them. But when they happen back to back, or when they happen regularly, or whether one side of the spectrum to the other, it becomes very difficult to manage and to be resilient, to those type of events. So I know we got a little off track from your question, but I want you to see how it may or may not relate. And, with these climate extremes are very important, and so are these climate normals. So this map here, this might be what you saw, but I interpret this as milder than average for the West, but cooler than average in the Pacific Northwest. It's a rather typical looking prediction of what you might expect in a La Nina, which is the cold phase along the equatorial Pacific Ocean of the ocean. Did you have any further question related to the winter outlook and what you saw on the news? Or maybe you're wondering how they come up with this?
I guess my question was like, do the Rockies make a big influence on the temperatures for between the West and the East?
Oh, in terms of the separation of like,
that was my thought from watching the news, that they just said it was going to be cooler on the West Coast and warmer on the.
I think I know what you're getting at. So with meteorology and weather, yes, the Rockies stop the cold air. They literally dam it up effectively in Montana, Idaho, and it has lots of trouble penetrating through Utah. And almost rarely do we get like Arctic air that makes it into California. And it does happen. It happened like in 1990. A lot of citrus was damaged. But the big Rockies, yes, they effectively stop a lot of the weather. Now, the weather that is largely more important for like an entire winter or an entire summer, or in this case, we're talking about winter, that type of weather let me see if I can go back. What caused this and what this does to our weather, it doesn't care about the mountains. It just doesn't care. And what caused this, the year 2 drought for Northern California, it doesn't care about the Rockies.
What caused that blob, that high blob?
And ultimately, we don't know. There's different theories. So a lot of times when you have repeated excessive years and years of warm weather, something has to compensate, something has to give. Typically, our ocean is very effective. You probably remember when you took science class, the heat capacity of water is much greater. It takes a lot more energy to cool water off and to warm it up. And so it doesn't change very rapidly. So typically what we look at is our ocean, and our ocean is a good absorber of excessive heat over land. Our ocean has been warming. So that theory is probably working. The ocean's probably doing its thing in absorbing all these hot years and hot summers and repeated warming and warming trends that we talked about in the West. But is it going into the upper atmosphere as well? That is also not likely, but that's possible. So what you might be seeing is the atmosphere not being able to dispose of all that excessive heat over the land. And the reason why that theory is possible, every single year, I shouldn't say every, but every year, in the desert Southwest, the land heats up when the sun angle gets high. The land is very dry, it's a desert. So the temperatures just get hotter and hotter and hotter. And what the atmosphere does is it compensates that, and it puts a big dome of warm air over the desert Southwest. We call that the Four Corners High. You might have heard that reference before. That creates a flow which develops the monsoon. The monsoon is the moisture thunderstorms that the deserts, that's like their only rainy season normally in Arizona, for example. So it's a very important season. So that natural cycle occurs every year. However, the ocean doesn't respond to the sunshine. The ocean could largely care less if the sun is shining on it. It's not going to change much, maybe a few degrees. It's not going to respond like land does. So what we could be seeing is not only is the ocean warming, but the ocean is not able to handle all this excessive heating that's been going on across the West, and it's resulting in this big dome of air or warm air. And the important thing about that, though, is that big dome of air, that's what controls our jet stream. So a lot of times what we see in drought and what we might be seeing with this overall warming is it doesn't just warm at our house, it warms at 10,000 feet. It doesn't just warm at 10,000 feet, it warms at 20,000 feet. So basically you have negative feedback. So the rich get richer, the warm gets warmer. And that might be what we're seeing, because there's really no other reason to explain it. And what is concerning, and I don't know if I think I included a map to show you an example of negative feedback. Yeah, I don't know if I included it. I might have it on this one. What I want to show you is the most recent ocean temperatures. Well, I can go to our, I'll go to our webpage. So you see that big dome of air that just hasn't gone away. not only does that steer our jet stream further north so that we have less storms and they miss us, it also causes the ocean to warm even further. Remember a few years ago, a famous NASA scientist started talking about the blob and you know, what that was and what it wasn't, and how that related to El Nino or how that didn't relate to El Nino type of thing. So what you're looking at here is a satellite view of ocean temperatures compared to, who wants to say it? What is it compared to? You got it, normal. So it's compared to a 30-year average of what ocean temperatures have been. And if you notice all this orange red in the Central Pacific and the West Pacific, probably not a coincidence that that warming, which was the blob in 2014, has now become a semi-permanent blob in 2021. It's been moving around, but it's been pretty persistent. So because of that dome of warm air that's ultimately pushed the jet stream north, and like we talked about, could be the result of excessive heat off of the United States, the West, the Rockies, everywhere. You can't just have repeated years of record warm temperatures. You can't just have climate trends and change and not have consequences in other parts of the atmosphere and other parts of the globe. So all that's been pushed north, and the result is the ocean is warming. So that's what I mean by negative feedback. So you have warming that's over land, that warms the atmosphere, that warms the ocean. They both try to resolve it, dissipate it. You have weather, which is supposed to resolve and dissipate it, right? That's what weather is. It transports warm and cold air across the globe, north, south, west, east, so that things balance out. That's what weather is. But what weather isn't is when you have these long-term trends or changes, warming that just won't go away, warming that is persistent. You might be wondering what this blue area is. That's the La Nina, Equatorial Pacific Ocean. La Nina and El Nino do exactly that. They relieve warm pockets of water and they relieve cold pockets of water. It produces upwelling, it produces changes in the trade winds. It's a very normal cycle. So the good news is El Nino and La Nina continue to do the thing. The bad news is that all this additional warming in the mid-latitudes where we live, the mid-latitudes, all this additional warming of the ocean and the atmosphere is likely why a lot of our El Ninos and La Ninas conditions are not resulting in the same temperature and precipitation as we once thought they were. If you remember the slide very early on, I showed, and you might have just been warming up, and so you kind of maybe ignored it. But even though El Nino is working, El Nino is not precipitation, it's not temperature, it's the ocean conditions along the equator. But we thought it helped steer the jet stream either towards us or away from us. But each time we think that, we have an event like 2015-16, the Super El Nino, and we're drier than normal. February of 2016 was the hottest February on record. So that didn't work. And then we have a La Nina like 2017-18, and it's almost the driest on record. So that's what you expect, right? But then we have a La Nina of 2016-17, a year before, and we're much above average. We're wet. We're equivalently wet to an El Nino year, which occurs a couple years later. So the bottom line is changes and trends of the ocean, the land, the atmosphere. It's all connected. It's all connected in one big cycle. It's all a fluid. It's all fluid dynamics. The changes that we're observing and the trends that we're seeing, unfortunately, are real and are not improving. Do we have other questions related to that? I know we're up to 7:30, so I promised you no later than 7:30. But I want to make sure if someone has a question or clarification that they chime in.
Yeah, can you, I don't know if I'm coming in and out, but I'm wondering on the precipitation table for, predicting precipitation, did it show that the west would have less precipitation in general and the east would have more? When you showed that precipitation table?
The forecast, yes, let's go back to it. The seasonal prediction. So this is not climate, it's something that hasn't happened yet, but yeah, it showed wetter than average for the Great Lakes, Midwest, Pacific Northwest. Seattle, for example, this is easy. This is an easy forecast because late November and early December has been incredibly wet in Seattle. The weather pattern has been so stagnant. So we just came from a record dry November, right? We couldn't get a drop of rain. Someone has to pay for that. And that was Seattle in British Columbia. They had record rainfall and lots of flooding, which you probably saw in the news. That may not be a trend, but it is a climate extreme. It's just like what we saw in Sacramento, where they broke their all-time rainfall in one day, just like what we saw Palm Springs currently right now as we speak is on pace to be the hottest calendar year on record. Not because it's a desert. That's compared to its own average. So Palm Springs is comparing it to itself, which is a desert. It's pretty remarkable. So that's the latest map there. Yeah.
I think the next two questions you answered about the heat dome and then about the explanation for the persistent upper atmospheric high that Mary asked. Did you, Carrie and Mary, did you have any more questions along that line?
Just one question, Pam. So the heat dome is controlling the jet stream, not vice versa?
Yes. So all the jet stream is by theory, is scientific theory. It's a thermal wind. It's a separation between cold and warm air. And that cold and warm air is created by the sun as it changes its angle through the season. So in the summer, the jet stream retreats north because the dome of warm air, just created by the sun itself, heating land, just becomes so massive, it shifts everything northward. Those are all seasonal normals. And so the jet stream is a separation of warm and cold air. It's called a thermal wind in science class. So when you have too much warming, what do you do to the jet stream? Yeah, you shift it north. And that is the long-term projections with basic global warming anyway, but yes. And then you have more extremes. So that's when people get confused because you have stronger cold air outbreaks, but they don't happen often. You have more persistent, longer heat waves, and they do happen longer and last longer. But then all of a sudden you get a strong cold outbreak and it's like, well, what heat wave, what global warming? So those extremes are vital to this whole, overall trend of warming. The extremes aren't going away. The extremes are going to get worse. It is basically the long-term projection. So so more severe cold, but overall longer summers, shorter winters, warmer conditions across the whole United States overall. But you still can have severe cold outbreaks like Texas last year. That's the challenging part. One event is not climate. 2 events is not climate. But when you have 100 heat waves or an entire season of warm conditions and only 3 days of very cold conditions, that is a trend in the warm direction. So unfortunately, these extreme events are the ones that are difficult to deal with, difficult to mitigate, difficult to prepare for, difficult to control, to contain. They're costly. They're costly, and that's why I showed that $1 billion disaster information in the beginning, because these extreme events, you know, which send an overall signal towards warming or drying. These individual extreme events, whether they're wet, dry, cold, or warm, are very costly, very impactful.
Leslie had one more question. She said, did you have an update on the convection conveyor belt in the Atlantic Ocean from Greenland to the equator?
I don't have an update on that. What are you referring to on convective conveyor belt? It seems like a lot of words kind of thrown in. From Greenland to, sorry, I didn't catch the last part.
The
Greenland
equator. To the equator.
I don't do a lot of work on Greenland. I assume, are you talking about the Gulf Stream? Perhaps?
My understanding is you know, you get up to the equator and the heat and the cold sinks to the bottom of the ocean floor, and it slides along the bottom of the ocean floor. It gets to the equator and it raises up. The hot raises, and then it goes across. It gets pulled back to Greenland. You have that whole conveyor belt, and they said that's a huge part of the nutrients that delivering for species. You know, and they said that's slowing down because of the heat of that conveyor belt. It's, you know, the temperature is becoming somewhat normalized and not extreme, is slowing that conveyor belt down.
Yeah, it's probably related to the natural Gulf Stream, but the natural Gulf Stream, which is a thermocline, you know, change in water temperature as you go below the ocean, and that stretches all the way up to basically Norway, from the Gulf of Mexico. But they're also probably talking more about the atmospheric part of it, not just the ocean part. And Greenland is suffering from severe glacier melt. And so that's probably where that is coming from. I don't spend a lot of time looking at that, so I probably wouldn't be able to add much value on what the latest findings are on that.
Thank you. I was just concerned if it's slowing down. They said if it slows down, it just shows that you don't have the extremes, the ice and the heat, creating that current.
Yeah, so remember I talked about negative feedback with drought on the land. Sun heats the land gets hot. Okay, big deal. You get rid of that heat by putting it in the atmosphere. Big deal. You put it in the ocean. Big deal. Well, if they all don't have any more room to absorb that excessive heat, then you have it spirals out of control and you have negative feedback. So the drought gets worse, the heat gets warmer, the rich get richer. So that is what we're probably seeing in the Eastern Pacific and what we see in the Western states over the past decade or so. So when we see less gradient, so like if the ice starts melting, which it already is, and you start exposing more land, so you warm that land. So now you have less contrast between that land and the temperature not only warms, but there's less contrast, less of a gradient between cold and warm, which is not good in any case, because that's what creates weather.
Thank you very much. What do you mean by rich get richer? I'm not following that. Thank you very much for your time.
It's just using a common phrase. I'm sure you know what I'm talking about.
Yeah.
Trust me, I'm
Um,
sure you know what I'm
yeah.
talking about. Maybe Google it if you don't know what I'm talking about. But thank you everyone for your great questions and attention. This type of topic, we can cover for 2-3 hours and still not cover all areas. And you still may have questions.
Yeah. Yeah, thank you, Alex. Yeah, I think this has been, one of the lessons is that it's always changing. I mean, climate change is all about change, and we've seen that right now. And I think that, I think I'm gonna just sign off and say, everybody have happy holidays and be sure not to buy any extra sweaters or coats for people for their presents this year. That's for sure. That was one lesson learned. Okay, well, I think we'll stop there and we'll see you in January. And we'll hopefully we'll all make it through this cold winter and the storms we might get to have. Thanks a lot, everybody.
Yeah, enjoy the rain on Tuesday. It might be quite a bit on Tuesday, so enjoy the rain Tuesday.
Yeah.
Thank you, Pam. Thank you,
Goody,
Alex.
we can experience a little winter.
Everyone.
Thank you.
Thank you so
Bye,
much.
everybody.
Appreciate it.
Bye.
My computer.
Very nice.
I know.
Bye-bye.
Bye.